Okay, the Mincer equations. Mincer equations.
Profe?
Sí.
I have a question about the ACF and PCF tests. I don't know. You have to distinctionize the system before applying them and having conclusions. Like about serial correlation and all that stuff. Or you have to do it before and after.
Okay. After you estimate the model, you have to use this test to check if the residual have zero correlation.
Yes, but what happens if it's not a time series? Like it doesn't have time series components, so you have to destationarize the model. Do you have to do that before applying those tests?
Yes, because the main assumption about this test is that the time series is stationary. Sometimes when the time series is not stationary, like it is integrated of order 1, you will see some is the word particular behavior in the ACF and the PACF. Okay, let me show you this first. For example, first, where's the difference? Then I will answer the question. Okay, we understand the difference between these guys. Okay, first the ACF. One way of computing the ACF is just by running a regression between YT and is lax. Okay, I'll put this in this. For example, the ACF. The ACF you have, this is just a sequence, right? Gamma. Okay. Gamma 0, gamma 1. Okay, gamma J. And gamma J is the covariance between YT minus J over the square root variance of YT. Okay. Now, when you run a regression between Y and X, regression. Then you have something like this, alpha plus beta X plus epsilon, where this guy beta hat is equal to what? How would you compute beta? Beta.
La varianza de XY sobre varianza de X.
Now let's try to do some analogy between these guys. They all look like, right? So this guy can be seen as the coefficient of running what regression? This is not the coefficient of running this regression between YT YT minus J. This guy is not rho J. Yes or not? Is it true or not that if you run this regression, the coefficient of this guy, YT minus J, is just the correlation of order J? This happens for every J greater than equal 1. So this is another way of computing the ACF, okay? Just running regressions and computing the coefficients. Alternative way of computing the ACF. Now let's think about the PACF. PACF. Okay, the PACF and the definition says that eliminates the PACF of YT and YT minus J is the autocorrelation that eliminates the effects of the intermediate values between this guy and this guy. What does it work? For example, the PACF of order 1 is just the result of computing this relation. Okay, this is the PACF of order 1. So it coincides with the ACF of order 1. Those are the same. But the PACF of order 2 won't be the same because it will be like this. Change it a little bit. Now, this guy is the PACF of order 2. But what is the difference between this guy and the ACF of order 2? When you compute the ACF of order 2, you run this regression. Constant plus just this lag. But here in this regression, you introduce the lag between this guy and this guy. So you eliminate the effect of this lag here. So the effect of this lag here is eliminated in this coefficient. Now, I want you to tell me how to compute the third order PACF. Jody?
Es poniendo los mismos componentes, solo que con este símbolo de 3 con gorrito y como que absorbiendo el primer y el segundo lag.
Okay, this is the partial. Okay, this is the PACF or third order PCF. And before I mention the Mincer equation, the Mincer equation are those equations that try to estimate the salary. Okay. Sometimes when we start to estimating the salary, we think about, okay, the salary must be a function of first constant plus beta of, what do you think? It could be the determinant of salary. A driver of the salary. Can you give me an example of driver of the salary?
Consumption.
Sorry, I couldn't hear you. Can you repeat?
Consumo, creo.
Again, please.
Consumo.
Salary consumption. No. What do you think? Experience.
Education.
Okay, good. Education. For example, if I just run this regression, someone can tell me, okay, but maybe you are forgetting to put some other drivers like the gender of the people, because we have seen throughout history that there is a gap between the salary between men and females, right? So the problem of if you don't include this gender variable in this equation is that the effect of the gender will be carried here and also here. There will be more variance here, and the coefficient here and here will be biased. So if you want to control or eliminate the effect of gender in the salary, you have to introduce and some other variables like, for example, age, so on and so forth. So that's what we do here. We're controlling.
Como variables instrumentales, así.
I wouldn't call you instrumental variables because these guys are not instrumental variables. Those are the variables that influence it in the salary. Instrumental variable would be like if you don't know for example, yesterday we were talking about people that smoke. Maybe we don't know how to either identify people that smoke, but maybe we can know that some people have what else? I forgot the word. Ceniceros at home. Maybe that's one way of using another variable as an instrument of the true variable, right? In this case, the gender is the variable that influences the salary, the age as well. Anyways, but those effects are clean from here. And that won't happen when you just try to compute the third order ACF. In the third order ACF, you just run this regression. This guy and this guy. T minus 3.
Profe, no entendí. Entonces el tercer orden de PACF son las variables no observadas que no tienen correlación con las dos primeras, ¿no?
The third order, yeah. PACF, you mean, right?
Ajá, sí.
Yeah. So you make sure that the effects of these variables that lags between this guy and the guy with respect to the one you want to compute the PACF are controlled, but by introduce them those lags in the regression. So this guy is clean of those effects. That is what is called PACF, partial ACF. This is the full ACF.
¿Cuál es el full ACF?
The coefficient of landing just the regression between YT
Okay.
and the lag. Just one lag. This is the full PACF, if you want to call it. If you want to differentiate those guys. Okay, this is the ACF and this is the partial because you are eliminating the effects of the intermediate lags. And the main function of these guys. Now let's go back to the slides. Is okay, this is the same that we have talked before. Is that we can use the ACF and PACF to make an hypothesis of what is the true data generating process of your time series. For example, if you are dealing with layer 1, okay, this is the ACF of an AR1 here on the left, and this is the PACF of an AR1. The coefficient in the AR1 is 0.7. That means that the process is an AR1 stationary process. And the ACF decreases geometrically, as you can see. The first term will be the same that this coefficient, 0.7, and then it will decrease geometrically. whereas the PACF will show just a jump in the first order, then zeros. That is the theoretical values of the ACF and PACF of an AR1 with positive coefficient. Stationary AR1 with positive coefficient. Okay. In the case of an AR1 of negative coefficient and stationary, the PACF will show as well the same value that is here, but in the opposite direction, because now it's negative. And the ACF also will decrease, but oscillating. In the case of the MA1, you will see the opposite of the, with respect to the AR1. For example, this is the MA1, the AR1, and now the ACF shows just one jump, and the PACF is the one that decreases geometrically. So you will see the moving average effects in the ACF with jumps, and the autoregressive effects in the PACF. The order, okay? And you also will see decreasing ACF and PACF in the autoregressive term and the moving average term. For example, here, this is an AR2. Because this is an AR2, you must see two jumps in the PACF. And the ACF should decrease because we have a negative coefficient here. It will decrease oscillating. Okay. But the oscillations won't be like this. Take more time to converge if you want, or oscillate. The period of oscillation will be longer. Now this is an ARMA 11 because it has an autoregressive and moving average term. You will see a bit coefficient in the first ACF and PACF. Now the ACF should decrease, and also the PACF. It's because the moving average, and this because it's the autoregressive process. So as a this is a summary of these properties in the ACF and PACF of any ARMA process, okay? For example, in a white noise, the theoretical values of the ACF and PACF should be zero because it won't show zero correlation. In the AR1, the ACF will show a direct exponential decay, while the first ACF will be different from zero, and the other ones will be zero. In the AR1 with negative coefficient, stationary, you will see that the decay is oscillating, and the first term in the PACF is different from zero, and the rest are zeros. and so on and so forth. Okay, any questions so far?
Sí, profe, yo tengo una. Si corremos, o sea, si ya tenemos el modelo y probamos a los coeficientes y no son significantes, ¿es white noise o no?
You have a model.
O sea, después de como que, o sea, ponerle arima, todo, o sea, ya como R o sea, ya tener como que el AR o MA model y, y corres, o sea, ya tienes el modelo y cuando te salen los coeficientes, el intercepto, a veces ahí hacemos como el p-value test, a ver si
Okay, let's say the model is this one. Okay. Sure. This is a true model generating, true data generating process. And then this question. No, you estimate this model. You have this. Estimate this guy. Also this guy. Okay, now you have these guys. Okay, just to make this model, this is a, this is not ARMA, this is AR1. Okay. Now you mean this coefficient? If this guy is
O sea, si ese coeficiente va a ser white noise, tendríamos que hacer como una prueba de significancia. Y si es, o sea, igual a cero, o sea, si se acepta la hipótesis, creo que es nula, sería white noise. A eso voy. O tiene que ser tipo cero, exacto.
okay. Okay. What you need to do is now after you run the regression and estimate the model, you have this is an innovation, okay? Innovation. Now this guy is not the same. This is the residual. What you need to check is if this guy is white noise. So you have to compute the ACF and the ACF of the residuals. In R, you just run this function, okay? And I will show you something like this. Maybe like this.
Profe,
Have to
hay
check that
un que no
these
pasa
guys are
intervalo de confianza, ¿no?
between the confidence interval. And the same here. And then you will say, okay, is white noise. Or because this is individual test, you can run the joint test. something like the box. To the residue. Okay, I don't remember what is the name of the function, but something like this. But you have to do it to the residuals. Okay, not here.
Sí, perfecto, me confundí porque salía el P, o sea, el de correlación igual a 0, entonces me confundí con eso. Gracias.
But before before estimating the model, also you can use the ACF and the PACF. And the PACF, you can use the ACF and the PACF to make an hypothesis of what is the true data generating process of your time series. Because if you have YT and compute the ACF and the PACF, and the ACF is like, let's say, it's like this. Then you will say, okay, this time series looks like an AR1, so I will run an AR1. That is before you know what is the model, because you don't know what is the true data generating process. Someone can say, yes, that knows that. But one way of making a hypothesis of this process is by running the ACF to the time series. Then you say, okay, this looks like this. So according to the table that our professor show us, okay, this looks like this makes, okay, I will run an AR1. Or maybe MA1 or an ARMA or ARMA PQ, whatever. So that is the usefulness of using the ACF and PACF before running the model. And after running the model, you also will use the ACF and PACF, but on the residuals to check this, to make sure that it is a white noise. The first line in this table. Ok.
Profe,
¿Mm?
profe, tengo entendido que cuando tú haces tu ARIMA y te salen los coeficientes, y a partir de ahí tienes que probar significancia y tienes que probar también que los residuos, como usted ha mencionado, sean white noise. Pero mi pregunta es, como tú ordenas por un criterio de información, acá o el que sea, por ejemplo, te va a salir supuestamente la mejor combinación de ARIMA, pero si es que esos coeficientes no te salen significativos, eso implica que las otras combinaciones de ARIMA, o sea, la segunda IC o la tercera IC que mejor explican el modelo, también son no significativas, o no necesariamente, tendría que probar con ellas para saber eso.
Not necessarily.
Ah, ok.
Because when you run the ARIMA auto function, it will include all the lags. I don't think some coefficient will be significant, I would say, because if though every coefficient, all of them are not significant, you are dealing with that white noise. Okay, that's it.
Claro, profe, pero en el caso, por ejemplo, que tengas un arma 2-2 y tú pruebas de que de esos 4 coeficientes que te salen, 2AR y 2MA, 3 son significativos y uno no lo es, ¿te quedas con la combinación de los 3 y el que no es lo eliminas o lo dejas en el modelo?
You can eliminate that coefficient, the term, because it won't add more information. Statistically, the coefficient of that term is 0. So it won't make any difference between keeping or just dropping it.
Ok, claro, claro. Pero, profe, pero en ese caso tú te quedarías con un arma 2,1, por ejemplo, y de repente ese arma 2,1 no es el 2,2 que era el que tenía el mejor criterio de información, el que te estaba dando la mayor modelada. Entonces mi pregunta era, si te quedarías con ese 2,1 sacando el que no es significativo, o te quedarías con el segundo que mejor modela según un criterio de información que tendrías que comprobar si sus coeficientes son significativos.
Okay, in the practice, that will depend on the selection criteria you have chosen before running the models, because when you develop models, you have to choose a selection criteria. Okay, that is before you run the model. So you put some rules to keep and drop models, to select the best model or the best models. For example, you can start with, okay, my first filter will be the information criteria. And when I run models using the information criteria as a selection criteria, I will keep just 5 models. Then, from those 5 models, I will keep with 2 of them that have the greater amount of significant coefficients. Then from those 2, I will check the one that makes better prediction out of a sample. Like I see. So that flow of how to pick a model, you have to make it before running the model. That is in the practice, because you have to be consistent.
Claro, sí, se me queda claro.
Okay, so when someone else comes to you and wants to validate your model, he will ask you, okay, what is the documentation of how you develop the model? Tell me what are the rules that you are using to select the models, because based on that information, it will validate what you have done and you're implementing in your work. So here, you say, okay, I have chosen 5 models, and my first model, the best one, I will drop it because it has, say, 3 insignificant coefficients, and I will keep the third one because it has more significant coefficients. And that's it. That's good, because that is your criteria. And if you do that over and over, that is your policy of selecting models. For me, it's fine.
Claro. Gracias, ya me queda claro.
Okay, so I will jump from this. These are the sample correlation. We have seen this before. Now we have this test on or correlation, the individual and the joint test. You have seen probably this with Gonzalo. We see the Bartle test in the ACF function when you run the ACF. Where is plot, right? This is the confidence intervals for this plot are the confidence intervals for the Bartle T statistic. Okay, and you have to box Q statistic, and you run it in R using the box test. I think that is the function. And as an argument, you have to put the name of the test, and you put box because there are two tests in that box text. What is the difference between the Bartle test and the box? The box is a joint test. Okay. The advantage, the problem with the individual test is that, for example, if you are using as a confidence significance level of 5%, you are assuming that 5% of the times, or in other words, 1 in 20 times, you will make a mistake, and you are good with that. That is a 5% significance level. 5% of the times, you will make a mistake, and you are good with that. So, because this is an individual test, let's say you run the test on 20 legs. Okay. First, second, third, fourth. Now let's assume that the confidence interval for the Bartle test individual test of the autocorrelation is above and below those autocorrelation. Okay, that doesn't mean those guys are zero, because you can make a mistake in one of them according to this alpha 5% significance level. That is the problem with the individual correlation test, because you're running the test for each one of these guys, and you can make a mistake, one mistake in over this 20 autocorrelation, because you are expecting that. And you are good with that. That's why you fix as a significance level 5%. That is the type 1 error. That's the problem with the individual test. In the case of the box, you run the test for all these guys for the n order, because that is a joint test. That is the main advantage between the Jumbox and the Bartel. Okay. Anyways, now you know what is the difference. These guys. Remember that the R square measures the proportion of the variation in the dependent variable that explain the dependent variable, the model. Okay, that is the R square. Since the R square can be written this way as 1 minus the variance of the innovation process over the variance of the time series. Okay. The R square won't say anything about the predictability of the model, because by construction, what is the variance of epsilon t plus 1? Okay. Variance of epsilon t, variance of yt. Okay, this is the model. Plus epsilon t. And we usually assume that this is white noise, which means 0, and variance sigma square. So this guy is sigma square. What is the variance of yt? To compute the variance of yt, we take the variance to the whole equation. Variance of yt equal to variance of phi 0, phi 1 yt minus 1 plus epsilon t. Okay. The variance of the sum of random variables is variance of a constant is 0. Variance of this guy times this guy is the coefficient. The square of the coefficient times the variance of yt minus 1 plus variance of epsilon t plus the double product, okay, is the variance between, the covariance between this guy and this guy. That is 0. The covariance between this guy and this guy, that is 0. Finally, the covariance of this guy and this guy, plus the covariance of the constant. Take it out, this guy and this guy. That is the variance of yt. What is the covariance between yt minus 1 and epsilon t? This is 0. Okay. Have you seen this before? The covariance between yt minus 1 and epsilon, this is 0. Or not?
O sea, porque es white noise, ¿no? Básicamente por eso.
No. That is because of this covariance between yt minus 1 and epsilon t. This is the expected value of yt minus 1 times epsilon t minus expected value of yt minus 1 expected value of epsilon t. Since this guy is white noise, it must be 0. We still have this term. Okay, here, what property can we use? We can use the iterating expectations. Okay, because these guys are the same. The unconditional expectation is the same that the conditional expectation, given information up to time t minus 1, and the expectation of this. Those are the same. Then we can take out this guy from the expectation because this guy is known at this time. Yt minus 1 of the conditional expectation of epsilon t. What is the conditional expectation of epsilon t given information at time t minus 1? Let's say this is the time, okay? This is time t, and this is time t minus 1. So you have information up to this moment. And then after a while appears epsilon t. There is any information here that would help you to predict the value of this guy or not? Now, since this guy is a white noise, even if you know this guy is uncorrelated with this. So there is no information up to time t minus 1 to predict the value of epsilon t. So this conditional expectation is the same that the unconditional expectation of epsilon t. And what is the unconditional expectation of epsilon t? That is 0. So this is 0 times yt minus 1, which means that this is 0. So the covariance between yt minus 1 and epsilon t is 0. Check. And if we assume that yt is stationary, the variance must be constant. Then we can solve that equation for the variance. Thus, the variance of epsilon t is sigma square. Then the variance of yt will be sigma square over 1 minus phi 1 square. That is the variance of yt. Then if we go back here, this is sigma square over 1 minus phi 1 square. Then the r square is 1 minus variance of epsilon t over variance of yt. If we replace those values in this equation, we have 1 minus phi 1 square, and this is phi 1 square. So the r square of the regression is phi 1 square. Okay, it's this guy. So let's say, what happens if the true value of phi one, the true value of phi 1 is, let's say this guy is 0.3. Okay. What is the R square for that model? What is the R square? Then the R square will be funny.
0.09.
Now, if you are in the concept in the context of econometrics one, what would you say? Okay, this is an R square of 9%. 9%. It's a good model according to that course. It won't be a good model, right? You will reject the model. You will throw that model to the can, to the trash can. But in this case, in the time series context, this R square is low by construction. It's not because there is more information. By construction, it will be low.
Profe, por esa razón se utiliza otros criterios, o sea, el Akaique, por ejemplo.
That's right. That's right. That's why we use other criteria to pick a model. So we won't see the R square. By construction, the R square will be low. Okay, there are more exercises here. You have to try to solve those. And on Saturday, I will help you with those examples, okay? Now, how to choose the best ARMA model? I told you there are different ways of selecting models. One way of using the mean square error. The mean square error is not other thing that here I forgot to comment pencil. Here must be 2. Okay. The mean square error is just the mean of the sum of the square of errors in the after the estimation of the model. Okay. So you estimate the model, compute the errors, then you take the average of those, the square of those errors. When the MSE is lower, that means that the model provides a good fit. Okay. By construction as well, when you increase the order of the ARMA, this guy, will never increase. This is like the R square. If you have a model and you add more variables to the model, the R square won't decrease. Okay. That's why we, instead of using the R square in econometrics one, we use the adjusted R square, because the adjusted R square considers the fact that you are using more variables and penalize models with more variables. That adds a few information to explain the dependent variable. So to avoid this overfitting generated by adding more lags in the equation, we have other metrics like the adjusted mean square error. So we penalize the previous metric by dividing the sum of, now again, probably here, this is square, by subtracting the number of variables or lags we are using from this guy. Okay. And there are other metrics now. Let me introduce you the information criteria that are based on the mean square error. Okay. And we have this Akaike, Hanan King, and the Bayesian information criteria. Those are computed using the mean square error and adjusting the mean square error by penalizing the addition of variables. The penalization term is different in each of these cases. Some of them have a more penalize more the mean square error. The one that penalizes more is the Bayesian. The one that penalizes less is the Akaike. That's why the Bayesian information criteria chooses the smaller models. And the Akaike tends to choose larger models because the penalization is lower here than here. And in between these guys, the most widely used are the Akaike and the Bayesian, okay? This Bayesian information criteria is also called the Schwartz Bayesian information criteria. Any questions, guys, so far?
Profe, una pregunta chiquita que es si es que los residuals te salen by noise, eso no implica que los coeficientes sean significativos, ¿no? Tienes que hacer esa prueba, sí o sí.
That doesn't mean that the coefficients are significant. Because the criteria is different. You see, the criteria here is you just compute the mean square error that depends on the fit of the model. How close is your model with respect to the true data? And that's it. Okay, that is the last slide. Yo creo que nos podemos quedar acá. Ay, ha habido mucha información, creo. ¿Está bien? Ninguno se ha desmayado. ¿Preguntitas?
Profe, sí, lo que le había comentado de cuando tenías en R la autoarima y te serían los coeficientes, pero ¿cómo podrías probar lo que le mencionó de significancia? No se me ocurría mucho, le había comentado si se podía hacer.
Lo que puedes hacer, mira, es